Good day, everybody. Let's take a look at certain topics right now, which will pertain to alcohols, their reactions, various transformations, and whatever else we can add. So in the timeline that we possess. All right, so let's start with problem number one. Which will be dealing with certain reactions of alcohols, right? And then we're going to have the structure here of the alcohol, which is going to be looking like this. CH3, CH. By the way, as you draw, so you can do lots of reviewing as you go, apparently. So for example, you can ask yourself, like, what's the CH3 called, right? So you can in this case, relate terms to like what they mean and what they represent, right? For example, CH3, it is an methyl, right? Methyl group looks like carbon with the 3 hydrogens attached to that, and carbon has also the free electron, basically, that can be connected to something else. It can be more complicated than that, how CH3 can be connected to something else. But for now, we just imagine that's okay. Well, we used to have methane, for example, then we removed 1 hydrogen from methane. So the hydrogen was removed with its electron and the CH bond was separated, right? So electrons from the CH bond were separated. So thereby, we have now free electron on H, which is available to be bound to like whatever is acceptable, right? And then we have also the free electron on the carbon from methane. And then this free electron on the carbon from methane now can be kind of like bound to something like whatever that is acceptable, right? So things like that. So a little bit of the rambling here, but anyway, so let's continue with our alcoholic structure. Bless you. Somebody sneezed right there. So, and then here we get it, right? So that's the alcohol. What kind of alcohol is that, right? You might ask yourself. So this is a secondary alcohol because the carbon that bears the OH group is connected to two other carbons here, right? So this one and that one. So then it is going to be a secondary alcohol that we deal with in our kind of like representation here. So now let's try to like look at the reactions, right, of the alcohol that can happen. And one of the popular ones that we can encounter will be the dehydration process, right? That takes place in the presence of H2SO4 as a catalyst. It is an additive, right? So this is a sulfuric acid molecule that we add, of course, like a bunch of molecules of that kind, right? So to our reaction mixture to make the reaction go like faster, right? And then to make it happen, basically. So then this is executed at the relatively high temperature, like about 180 degrees Celsius. And then we're going to this, in this case, under these conditions, H2SO4 and 180 degrees Celsius, we're going to perform the dehydration or a removal of HOH, H2O, water, in other words, from the molecule of alcohol. How is it done? So you can like take a look at this OH group that will be removed, right? And then the hydrogen will also have to be removed from the adjacent carbon to the carbon that bears OH. What's adjacent? What's adjacent, right? So not this carbon, not that carbon, but we have 2 adjacent ones, right? So these are carbons which are directly connected to the alcoholic carbon. So this one and that one. So they both are directly connected to the alcoholic carbon. One bond direct connection, another bond direct connection. So then next what happens? So is the removal of the hydrogen either from this carbon or that carbon, right? Granted, they both have carbon, they have hydrogens to remove, right? So now let's see what happens. So we can have like 2 distinct products if you draw the structures, right? So now we'll have like option A, which will be looking like this. So let's say we're removing the carbon, or sorry, not the carbon, but the hydrogen from the leftmost carbon, right? And then instead of CH3, we're going to obtain CH2. So CH2 will be obtained. So apparently we'll have this kind of like still the single bond will prevail, right? So now, but now, so we are going to be careful, right? So we're going to have CH without OH. So now we're going to form like this like free electron, right, after the removal of OH. So that's one way to imagine that. Of course, the mechanism, that's how this happens in detail and in reality is a little bit more complicated than that, right? So, but for now, so we are just going to be concerned with the formation of the bonds, right? which are based on electrons. And for our simplicity of this introduction course, we are going to just like think about the electrons which are liberated after being separated from the bonds, right? So, or separated from bonding or liberated from bonding, something like that, right? So anyway, there used to be an electron, let's put it here, right? So, but this like topmost electron will be able now to form the bonds. So once we remove H from here with its respective electron, we are going to liberate an electron on the carbon, right? So that's kind of going to be our approximation, right? So which kind of is not necessarily true in reality, right? So, but it will drive us to at least the correct product, right? So that's what we're going to be concerned with right now. So we are going to be thinking about the bond breaking and the bond making. So then this bond will be made. So now you have your alkene part, right? So then everything else stays. So CH with a couple methyls. So that's one option, right? So then another option, we're going to remove the OH and then the hydrogen from this carbon, right? So from the like rightmost carbon, so to say, and that's what will happen. So another product can be formed. So CH3 will stay, right? Let's say it will not lose an hydrogen. CH, of course, will lose the OH as usual. So that needs to be done. So then we'll have CH here. So now the free electron is generated on the CH, which will be like available for the bond making. So also the free electron is generated on the, sorry, I need to erase this hydrogen, by the way. The free electron is generated now on the carbon here, and this one, right? So because the H is gone, right, with its respective electron. And now we're going to make the compound like that. So now we made two different alkene isomers, right? So now which one is going to be the major product? That's the question, right? So the rule here is Zaitsev's rule, right, which says that the alkene with the most carbons attached to the sp2 hybridized carbons, so will be the major product, right? So we have here sp2 hybridization going on, sp2, right? So then we have in this isomer, we have sp2 here and sp2 there. So now let's count the carbons which are attached and then circle them with some sort of like different color circles, right? Maybe let's make it like orange or orange, right? So here we go. So let's count the carbons. So here total we have 0 carbons on this carbon, sp2, right? So and then on this carbon we have direct attachment of only one other carbon, right? So we have one circle. So basically we count the attached carbons to the sp2 hybridized carbons, the total number of attached carbons to the carbon-carbon double bond locus is going to be 1 carbon, right? So here we go. Now structure number 2. So here this sp2 carbon has one other carbon directly attached to it. So this sp2 carbon has 1, 2. So the total number of carbons attached to the couple of carbon-carbon to the carbon-carbon double bond, rather, is going to be 1, 2, 3. 3 is more than 1, so consequently, this is going to be, this like a lower structure will be our major product, right? So it's going to be our major isomer that will be formed. So maybe, so basically it's going to be like prevailing, right? It's going to be higher percentage of this isomer on the bottom that will be produced. So here, you can typically you cannot say that it's going to be like 100% formed, right? So we always need to suspect that there is going to be some admixture, so to say, of the like minor product. This is going to be the minor product. Maybe it's going to be like 15%, maybe 1%, 0.5, right? So, but the point is that this is going to be the major, right? So not like absolute, right? So it's not going to be like one and only product that will be formed. So in chemistry, in reality, in real chemistry, and like in the like lab and whatnot, right? You are going to deal with the purification of the resultant product. So because there is going to be something like additional going on that is formed in the minor form, maybe 20%, maybe 1%, but still, right, it's going to be there. So, and then you'll need to get rid of that via purification methods of some sort, right? So, and then this one will be like a minor product. So, but if somebody asks you, such as me, right, on the exam, so what's going to be the major product? That's going to be this one. And then plus, if you want to explain it, I have the explanation. I had the explanation right now, right? So anyway, so that is our dehydration process in detail with the Zaitsev's rule applied to justify the results. All right, so now we're going to move on to our next problem, which will be about the ether formation, right, from some sort of random alcohol. So let's take a look at what takes place there and try to predict the ether now. So problem number 2, so we'll be looking like this, right? So we have some sort of relatively complicated alcohol that will contain a phenyl substituent, right? So then we'll have CH2, CH2OH. So it's going to be just one alcohol which will undergo the ether formation, right? So ether formation, how does it happen? It happens at the presence of H2SO4, right? So which is going to be our common like dehydrating agent. So if you recall how the ethers are formed from, let's say, like one specific alcoholic molecule, you will recall, hopefully, that there is going to be a water molecule formed, right? So water molecule will be formed as a byproduct alongside with the major product or the main product, which is going to be the organic molecule of an ether of some sort, right? So this is typically held, the synthesis is conducted at a little bit lower temperature than dehydration, 140 degrees Celsius, right? So then we're going to make the ether. So yeah, for your convenience, what you can do to assist with your like learning, right, how the ethers are formed, show another molecule, identical molecule of this very alcohol, which will be looking like this. So now what you're going to do is circle in the orange, right, in the spirit of Halloween, the groups which will be kind of like removed, right? So, and then the leftover uncircled groups will be connected. So the H will be removed. Consequently, you're going to have here the oxygen with the free electron, right? So for our like imagination purposes, let's say, and then here you're going to remove the OH group. So, and then you will have the carbon with the liberated electron, right? So for our bond making purposes. Of course, once again, right? So the real mechanism can be a little bit more complicated, right? Maybe you'll have some kind of like organic ions formed here, right? So protons, hydroxides, and so on. So, but for now, we're just going to be driving towards the bond formation, right? So again, from the review perspective, so what's a bond, right? So a covalent bond, specifically, it is the one which is made up of two electrons, right? So one electron on one atom, like in the group of atoms of some sort, right? Some kind of group, substituent and so on. And the other electron will be like hosted by another atom or the group of atoms, right? So yeah, basically that's what we have here. So those two orange electrons will be now making the new bond. And yeah, HOH will be released. So you will have H2O as your byproduct, right? So, but the major thing is going to be this, right? So we will redraw this part with an oxygen and a free electron on it. Okay, so then we'll redraw this part with the carbon with a free electron on it. I'm just going another way, right? So I'll just flip the structure for the drawing purposes. And then we go. I get something like this. Okay, so now we have the bond. So that's your polar covalent bond, right? If you think about it, so it's composed of two electrons, but different atoms of different electronegativities will contribute into here, into the bond formation, right? So we'll have the polar covalent bond, and it's going to be polar because carbon is less electronegative, excuse me, than the oxygen. Oxygen will be drawing the electron density towards itself because it's more electronegative. You can show the like dipole moment here, right? So things like that. So again, that can, these questions, right, as you ask yourself, the detailed questions can assist in your like review process and yeah, kind of like knowledge refreshment, things like that. So yeah, basically now we form our ether, right? So we have the COC motif here. So that's kind of like the one. And then if somebody asks you, what's the function group? It's COC. So that's an ether, not ester, but ether. So like make sure that you kind of like grasp this difference. And yeah, this is your like big ether right there, right? So we're not going to necessarily name it, so because it could be complicated for our pay grade. So, but the point is that, so what we can do legitimately is show the structure, show the conditions, right? There is already like a lot of things to do. So then we can show the Lewis structure things, such as the lone pairs, right? So on the oxygen will have two bonds, and two lone pairs will be also present on the oxygen atom in the ether molecule. All right, so that's our problem number 2. So now let's move on to the next one. So I'm going to erase everything, and here we go. So problem number 3. So what is that about, right? So we're going to have a look at some further um, reactions, right? So, and in this case, in problem number 3, we're going to like move backwards, right? So to say, right? What do I mean by that? So we'll show the product, and then we're going to predict the reactant, right? So that's going to be needed in order to form the respective product. So, and the reactions will be looking like that, right? So we'll have some kind of like X reactant, right? So then we'll have some kind of like Y conditions, right? So these are unknown things. And then all of a sudden, we're going to form the molecule, which is looking like this, right? So, sorry, not this. So what are we doing? So we are forming the ketone molecule, by the way, right? C double bond O, C. So this like motif tells you that you have a ketone as a function group. You can also look at the smaller function group, which will be C double bond O. And then this group is known as a carbonyl group, right? So yeah, that's kind of like what we see right now, right? As we like investigatively ask ourselves, so like, what do I see in front of myself, right? So then our next step will be to take a look at this, right? So where do ketones come from according to our like current knowledge, right? So they can come from secondary alcohols, right? So which are oxidized and the ketone is obtained, right? So the respective secondary alcohol, what should it be like, right? So you have to have the carbon, right? So that is would bear the OH group. And then this carbon with the OH group should be attached directly to two other carbons. So, and then from this thing, right, from this motif, we can imagine the secondary alcohol, right? So we just need to turn this ketone into the secondary alcohol on the left side to generate our reactant, right? So let's go ahead and do that. So we'll have CH3 intact, CH2 intact as well, and then this carbon will undergo some changes. Oxygen will still stay, right? So then to make an alcohol out of that, we have to have OH, right? And we have to have here H. So now 4 bonds are engaged on the carbon, right? So then we have the OH and that's all, right? So we have our secondary alcohol, which upon oxidation will give us the ketone. So let's show the oxidizing agent here. That's it. Right. So again, so if you want to kind of like fast forward this reaction, so you will be removing this H and you'll liberate an electron, right? And you'll remove this H and you'll liberate an electron. So those two electrons will be connected, right, into a bond to make this like bond right here, right? And then as a result, you will make the respective ketone, right? So things check out. So secondary alcohols oxidation leads to the formation of ketones. So now let's take a look at the other type of alcohols, right? So that would lead to the formation of other products. Okay, so we're moving on. So to problem number 4. A little bit of meditative erasing going on. All right, so here we go. So now it's a new thing, X something something, some sort of conditions, and then all of a sudden we are going to obtain a carboxylic acid of this kind. So that's the one, right? So C double bond O, C single bond OH, attached to the carbon of some sort, right? So that's going to be the carboxyl group, carboxy group, carboxylic acid, right? Functional groups. So these are all synonyms for this kind of like formation of atoms. So now let's think what's going to happen, right? So this is done via the oxidation of the primary alcohol, right? So you need to have the primary alcohol, and then you need to have the strong oxidizing agent in order to kind of like go, as you recall, from alcohol, primary alcohol, to the aldehyde, and then to the further oxidized compound that will be the carboxylic acid, right? So aldehyde will contain the only one oxygen in its functional group, and carboxylic acid will be looking just like aldehyde, except it will have an extra oxygen, right? So that will be like between carbon and the H. So yeah, essentially that's what it is, right? So you can draw them side by side, and then you will see there is like a minor difference, like one atom difference between the like aldehyde functional group and the carboxylic acid functional group. So here we go. So let's show the reactant, right? So this will stay intact most likely. So let's just redraw that. And then this is going to be the carbon that will undergo the oxidation, right? So we'll have the primary alcohol. Tetrahedral carbon, by the way, geometry-wise, right? So that's the one. So we have 1, 2, 3, 3 carbons, right? So mind your, what's it called, count of the carbons, right? So not always you'll be able to like balance those reactions, right? So because we don't show other like more complicated products that are formed as a result. So yeah, but typically don't like lose carbons all of a sudden, right? In the events when you don't need to lose carbons. So here we go. That's the oxidation process, right? Here, so strong oxidizing agent. So it's going to be strong oxidizing agent, SOA. So will be applied to jump from alcohol straight to the carboxylic acid, right? So 3 carbons will be still present. So, and then this carbon here with this asterisk will be now converted into this carbon, right? So basically alcoholic carbon is turned into the carboxylic acid carbon right here. So we do the oxidation here. We increase the number of oxygen atoms, and we also decrease the number of hydrogen atoms, right? So this kind of like all manifests our oxidation in organic chemistry like fields. So yeah, that's it. So yeah, if you notice, so that's what happens here. So basically what can we say? Like we remove essentially this hydrogen, right? So maybe that hydrogen is gone as well. So, and now you are adding what? So you are adding the double bond, right? So that now turns into the carbonyl eventually. And then you are adding the OH here to this carbon with a star, with an asterisk. So that's it. So that's going to be your oxidation process right here, right? So as we talked about that, it's going to be a good idea to kind of like show which like hydrogens and stuff are removed basically, right? And then what is like added in its stead, right? So, but basically, no matter what kind of like primary alcohol for now you will take, right? Maybe there's going to be something like more complicated than an ethyl group, maybe propyl, I don't know, like tert-butyl, sec-butyl, some sort of like phenyl group, right? So it doesn't matter. So you'll just be kind of like going from like R. Let's imagine this is an R group, right? So something like R, whatever, right? So, and then this like CH2OH will be turned into COH. So that's your kind of like blueprint pattern, whatever you might call it, right? That tells you how to convert the primary alcohol into an acid using the conditions, right? Will be strong oxidation agent. If you use the mild oxidation agent, for the alcohol, primary alcohol oxidation, you will first obtain the aldehyde, right? So like on your own time, you might as well show how to obtain the aldehyde from this very alcohol by the action of oxidation against this carbon with an asterisk. So yeah, basically you will make the aldehyde, which will be exactly the same thing, except you will not have this O, and you have direct connection between C and H. That's it, right? So those are problem number 4. So now let's move on to the next piece in our exploration, and that's going to be problem number 5, right? So we're going now to do another oxidation, actually of the primary alcohol. Well, so some alcohol to the ketone, no, to the aldehyde. So that's our things, right? So some sort of like reactant that we need to show under certain conditions, and then we're going to obtain an alcohol that will be looking like this. Sorry, not an alcohol, but this compound, right? So which is containing this functional group. So yeah, it will have this like alkane part and everything, right? So, but this is something like more exciting, more diverse in terms of the like atomic composition. So we have here carbonyl with H, right? So that's going to be an aldehyde group. And then you have the like aldehyde molecule of some sort, right? So this is obtained, as we recall, upon the oxidation of primary alcohols using some sort of mild oxidation agent, MOA, right? As we kind of like abbreviated. Let's show the respective primary alcohol. So this atom used to belong to the primary alcohol. So we just need to turn this into the primary alcohol, right? So let's do that. We are going to form our reactant now. The alkyl chain stays. And now this turns into the primary alcohol, right? So what do we do here? So it's going to be looking like this. It must have OH, right? And then we'll just beef up this carbon with H and H, right? So that's it. That's your primary alcohol. So that's the locus where the reaction takes place. So then you kind of like preserve this carbon, right, which will turn into the carbonyl carbon, right? So just like try to use those professional terms, so to say, for your own good, basically, right? So because you want to get some value from this course and yeah, use it in your future, one way or another, so to a larger small extent, but yeah, hopefully this is useful, right? So then at least we'll try to make every effort to make it useful. So then what else do we have, right? So we're going to basically remove this H, remove that H, and then you are going to form one new single bond, right? So by means of those like liberated electrons on the carbon and on the oxygen, which will make you this like pi bond or something, right? So that's like the way to think about it. And yeah, so that's for now. So we're not going to be concerned with the mechanisms, how exactly the electrons are moved, right? Because it's more complicated. It's the next step in explorations, right? If we get there ever, so, but maybe it's going to be enough for you, and then you'll be okay, well, thank you, no more, right? So, but basically, so think about the electrons, right? So at this point, it's like very clearly we can represent them. And for your review purposes, you can just redraw those structures, maybe like color code the electrons, which are present in the broken bonds, and which will be forming the like new bonds, right, in your products. So yeah, again, so you can like do the review yourself here as well. So yeah, that's like the thing, right? So here again, conditions, we'll have the oxidizing agent, and then we'll call it the mild oxidizing agent, mild OA, mild oxidizing agent will be present, right, to convert the primary alcohol into the aldehyde. All right, so yeah, that's as far as those things are concerned. So now we're going to move on to the next problem, which will be problem 6. And potentially that's going to be our last problem, like not to take out the brain too much. So on this glorious day, so but we are going to still deal with something. Problem 6. Okay, so which will be multi-step synthesis, right? So what is a multi-step synthesis? That's when you have some sort of starting material, some chemical, right? So, and then it undergoes reaction 1. So you make like chemical number 2. Then chemical number 2 will undergo reaction number 2, and it will make you chemical number 3, right? So that's what the multi-step process is, right? So generally, you might encounter that somewhere. So like, I don't know how your professional life is gonna unveil, right? But anyway, so this is the general scheme of a multi-step process, A to B, B to C, right? So you have two reactions, reaction number one, A to B, reaction number two, B to C. And here you have like, okay, chemical A, chemical makes chemical B makes chemical C. So that's your simplest multi-step process, right? So like that can be like envisioned. So in a schematic fashion, that's as far as the schemes and principles go. So now let's take a look at something more tangible, which is going to be the actual chemicals that undergo transformations in order to make the stuff that we want, somebody wants, whatever it might be, right? So let's take a look at something specific. So we're going to start with an alkene, which looks like this. One butane, by the way, so you can also like try to assign names to something, right? So you'll just like sound more professional, or at least say it's an alkene, right? So don't like forget the name of the like class of the compound. That would be like not so good, right? And then from this alkene, you are going to make, even though you don't know how to name it, right? So right now it's going to be a ketone, right? At least you can acknowledge that you can see a ketone there. So we're going to make a ketone from an alkene, right? So we are not aware about the reaction, right? That directly gives us like ketone from an alkene, right? So we need to think about it. What happens, right? So this ketone, how can it be formed, right? So we had like a bunch of reactions at this point, and then we need to try to recall, right? So maybe we can flip through the slides, notes, and so on, right? So, but the ketones can be formed from secondary alcohols, right? So we need to have the alcohol that precedes this ketone. So now we have the alkene, right? So we have the alkene, we have the alcohol now in our mind. So what's the connection between those two, right? So we know as well there is another reaction that exists, which is basically the hydration of alkenes that gives us alcohols. That's it. So these are your two reactions. So now let's perform the first one. The first one will be the hydration, right? Which is going to be done by the addition of H2O molecule in the presence of H2SO4 to the molecule of an alkene, right? This will undergo the Markovnikov's rule, right? Which will say that H from the HOH will go to the sp2 carbon, right? So this is sp2, by the way. Lots of review going on, right? So the H from the HOH will go to the carbon on the double bond, right? So with more hydrogens. So H will come here, OH will go there, right? So that's it. That's going to be our product. And then, by the way, we're going to form the secondary alcohol. That's another way to show the CH3 or a methyl. Then we have our methine, right? So with OH. That's your secondary alcohol. So next step will be like this, right? So this will lead us via the application of the oxidizing agent, right? So O in brackets, we're going to form the respective ketone. We will be removing the what? H, and we'll be removing H, right? So, sorry, not this one. So that one will be removed, right? So, and then the liberated electrons will be able to form the new bond. This one, let's imagine, between the carbon and oxygen to yield a carbonyl, right? Which will be an integral part of the ketone function group. So that's your multi-step synthesis right here. So yeah, using the time, let's take a look at another multi-step synthesis, right? So which is going to be problem number 7, our ultimate problem of today. So here we go. A little bit more challenging, right? So, but again, so we are going to use the reactions that are already present in our current armamentarium of reactions, right? So CH3, CH2, 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 OH is going to be turned into a ketone again. So this tells you that using chemistry, right, you'll be able to start with like various materials, right, in order to get to some kind of like the same target material, right? So as we can see. So here again, so we are going to form the ketone, which is formed from the secondary alcohol. Over here, we have the primary alcohol, right? So we need to somehow turn it into the secondary alcohol. How do we make an alcohol, right? So typically we have seen so far just one reaction, right? It is the alkene hydration, right? So we have here the alcohol. How do we go from this alcohol to the alkene, right? So that will be used to make the secondary alcohol. So in order to make the alkene, we need to dehydrate this primary alcohol, right? So let's do the dehydration process, right? Which is going to be executed in the presence of H2SO4 at relatively high temperature of 108 degrees Celsius, right? So dehydration here will be kind of like only one option. OH will be removed from this carbon. And what did I write here? So, oh boy. Yeah. Whereas the hydrogen will be removed from this carbon right here, right? So that's the hydrogen removal. So now we're going to, these carbons are too far, right? So with their respective hydrogens. So we're going to form the alkene. Let's see what we're going to form. Liberated electron, and now this CH2 turns into CH because it lost one of the hydrogens. So now we're going to make the bond, right? So that's your one butene again, right? So CH, double bond, CH2, and everything else like is copy paste. So now we're going to make the alcohol out of that. So how to make the alcohol? By means, again, of addition of H2O, hydration, right? At the presence of H2SO4. So the alcohol formation will follow the Markovnikov's rule, which says basically the hydrogen again will go to the carbon in the previously existing double bond, right? It will go to the carbon with more hydrogens, right? So hydrogen will come here and the OH will come here. So we're going to form the secondary alcohol as we may envision this in our brains. All right, so now let's turn this into the ketone. So we'll use the oxidizing agent, and then we're going to remove this H and that H. Liberated electrons will form the new bond, which is going to be this guy right here. And that's it. So we'll form our target ketone, right? So here we have three reactions. So that's quite a record for us. And then this is another example of a multi-step process. So yeah, those are pretty good, right? So especially when you want to, maybe you can generate something like on your own, right? Start with some kind of like target material and try to fit the reactions knowledge that you have to date in order to generate that magnificent target material, right? So that's just some suggestion. So based on this problem. So yeah, anyway, so that's as far the multi-step synthesis are concerned. So we are going to talk about thiols in the future. So, but for now, I think it's time to stop and continue with other activities. So yeah, that is it for now. And I thank you for your attention and attending this tremendous video. Have a good day, and we'll see you when we see you. Bye.